So the Leaning Tower is one of the things, but Pisa is also a place for elite universities and great deal of activities in mathematics. For example, Professor Marco Romito is a student of Franco Flandoli, and he is in University of Pisa, Italy. He has worked on deep aspects of stochastic analysis and Navier-Stokes equation, connecting controllability, ergodicity, hyperellipticity, and things like that. So he will also go slowly, like Ravi did, and explain us some good things. So the talk now switches to stochastic analysis area. Let's welcome Marco, came all the way from Italy.
Okay, I keep this, so if I don't remember something, I have a look at the notes.
Oh, the mic.
And the mic, yeah.
Can I check whether it's on? No.
I should switch it off probably.
Yeah.
Down that. Okay, thank you for the presentation. And I should first thank for the invitation, but the presentation was so impressive that I felt compelled to thank first for that. Okay. The topic of my talk is, as you got for the title, densities for the Navier-Stokes equation. Okay. I will speak in 4 parts, and let me make a scheme of the 4 parts. So in the first lecture, what we will see is, well, a few motivation. I mean, why one should be interested in getting densities, and a quick glimpse of the setting of the problem. As far as I understand, some work has been already done, so I can just take it for granted. I will talk about anyway that setting, just to be sure that the notation I will use and the notation you are getting used to in these days are almost the same. And then we will start getting an idea of the difficulties, and we will talk about the problem of the reference measure. Now this is not very clear, but you will understand why I want to talk about this. So in the second part, tomorrow, I would say, we will give some ideas on equivalence of measure. And essentially why equivalence of measures is more difficult in infinite dimension. And we will see some existence of densities by means of the Girsanov theorem. And if time allows it, some idea about positivity of the density. And positivity is a topic which essentially is done by means of theorems of control. And in the third part, I will talk about densities through Mallavan calculus. And I will first tell you what is Mallavan calculus. That means essentially, if you already know it, fine, and you don't need what I will say. If you don't know it, you won't get what it is by my words. I'm not very a specialist on Mallavan calculus, so I will give the simplest explanation I can devise so that one gets the ideas without getting all the complication of the calculus. And in the last part, we will see other methods. Because at some point, I will convince you that the problem I'm studying, in a way, cannot be treated by Mallavan calculus. There is a deep reason for this, which is related to the fact that in dimension 3, no one knows how to prove uniqueness. Okay, and in the end, is also an explanation on why a solution of Navier-Stokes in 3D do not have a Maillard derivative. And these other methods will be some, yes, on the Fokker-Planck equation. And then also a technique which I introduced in collaboration with Arnaud Debuche from Rennes, which I know, work in collaboration with. Indeed, all this lecture, in a way, started from this work, and then I added a bit of other stuff, and say today, tomorrow, you will find the notes on the web. And there was a misunderstanding, you know, things like forgetting to put an attachment, and so the notes are not yet ready, but they are ready. I mean, I have them, and you will have soon. They are not really complete. There are a few paragraphs that are missing, but you won't miss some. Okay. I should go faster. Okay, fine. Okay, so first is what kind of densities we're talking about. Okay, first I want to study the Navier-Stokes equation because essentially, since the beginning of my career, I've been fascinated by the problem of uniqueness for the Navier-Stokes. I don't want to prove uniqueness for the PDE equation. It's not me. I mean, I'm not the kind of guy that has the good techniques, the good knowledge, and also the good, the one thing that is missing to prove uniqueness for Navier-Stokes. But I'm more fascinated by the problem of uniqueness of laws for the noise force Navier-Stokes, which anyway is still an open problem anyway. So I won't solve it. And so getting densities. So we have an equation which is a stochastic equation. And stochastic equation is a process, and so is a family of random variables. And these random variables have a law with respect to, and if this law may have a density. So a first good motivation to understand if these random variables have a density is that this gives us a better knowledge of the random variable itself, and so of all these main characteristics. So I mean, this is a very general motivation, which I say that now we can even forget. There is okay, now the way I show you is kind of a toy thing, but I'm a pure mathematician. I mean, so no way to say anything different. But if you want to do experiments on fluids, so what you do? There are some techniques to do this. I mean, one is to, in a way, it is like a Lagrangian method. You put some particle, you follow the particle, and then you get data from these particles. Or you may use different ways. For instance, some kind of infrared or other kind of radiation. You look in some way at the fluid, and by different measurement of the quantity you want to measure, like heat or things, you may get the velocity of the fluid. Or you have some kind of, I don't know, machine that sits in one place and measure the velocity of the fluid particles that hit the machine. Okay? So I want to stick on this third method. So what you do, you have your box with the fluid, and then you have your machine, maybe more than one. Okay? And well, you want to measure the velocity. And so if you do this, what you do, you sample the velocity of your fluid at some points. Okay? x1, ux, some d. Okay? And then this, if you consider that, okay, I don't want to consider the error, in the statistical error in this measurement. I mean, this is not what I'm doing because this error is part of the experiment. But you may think that in the evolution of the fluid, there is some statistical error that comes from, I don't know, heat fluctuations. And so it's reasonable to have a random term which evolves, because then you have some heat fluctuation somewhere, and then this propagates. And so you may have, that's why, I mean, one can consider the Navier-Stokes equation with a random term. Okay? And so in the end, even regardless of the statistical error in the measurement, you still have a random variable here. Now I want to convince you, in a very simple way, that this is so sampling a random variable, and which is not, well, this is clear, this is not the full velocity, but it's only a part of it. And after this, I want to convince you that it's reasonable, rather than studying the full densities for each random variable solution, I mean, say evaluating the solution at some, in some initial condition, just to consider only projections of the solution. There are two very good reasons for this. One is I can only do that. And so this is a very good reason. And the second one is essentially it comes from this example. It says that in a way it's reasonable to look at projection of the random variable and hence the projection of the densities. Because in real life, that's essentially what we see. So how it works here? Okay, let's say that this is a periodic box. So I'm just making all ideal. So this is a periodic box. And so I can write the solution in a Fourier series. Okay? So this is U is UK EI KX. And K is sum over Z, 2 or 3, doesn't matter. I mean, let's say 3. And okay, and so I want to compute U in X1. And this is UK AIKX1, which now I can write as, say, an infinite dimensional scalar product of the UK K in Z3 times EIKX1 K in Z3. And so essentially this UX1 is the projection of the solution over this vector. Okay? And if I have more than one, it's like writing this random variable as a projection over the family of vectors, this one, the infinite dimensional family, the family of infinite dimensional vector EIKX1. Okay, what? Okay, so these are vectors in some infinite dimensional space to make everything reasonable. I mean, I want these to be points in some space, and so H minus 2 minus something would be fine as an infinite dimensional space. So I'm thinking at this kind of space, minus 2, minus 3, say minus 2, minus something. And this something can be big if necessary, if I didn't make the computation correctly. Okay, so these are elements of this huge space. And if I consider this family, and I can see this as a projection onto the space generated by these vectors. Okay? So in a way, I update the object of my analysis, and the object of my analysis is getting densities for those random variables which are obtained by means of projection of the solution. This projection can be, now here this is the example is simply a projection onto a subspace. But in a way, at least in some case, essentially this one can also consider finite dimensional valued functional of the solutions. Well, we know we already seen several of these functional. For instance, the energy. So if I consider the L2 norm of the solution, this is a good finite dimensional valued functional of the solution. I compute the density, I compute the energy, and if this energy comes from the stochastic PDE, this is a random variable. And so one can ask if this random variable has a density, and the density, since it's one dimension, is R valued. The natural reference measure for finite dimensional measure is the Lebesgue measure. Okay, and so one can ask if this random variable has a density with respect to the Lebesgue measure, and that's what we will do on Wednesday. Okay. I hope I will be able to convince you that studying finite dimensional projection is easier because in infinite dimension there are a few problems. One of these is the fact that we do not have a reference measure as good as the Lebesgue measure. You know, Lebesgue measure is flat, and that means that in a way it does not add any bias on what you study, because it does not give any privilege in any other area of the space. And in infinite dimension you don't have such a flat measure, at least it's a meaningful flat measure. I mean, so okay. So this amounts as an introduction to the problem, which is why we will, in the next days, we are going to study finite dimensional projections. First, because it's, in a way, it's the real thing you observe on the fluid. I won't explore this. I mean, this is just, for me, is a toe explanation. And because there is a reference measure missing, and okay, and last but not least, is what I can do. I can't do anything else on infinite dimension. Although understanding densities for infinite dimension would be, in a way, at some point, I believe that this was a key point to go through uniqueness of laws. Doesn't work, but. And let me see, it's 4:50. Is I go on to 5:30, right? Okay. So a reason for studying density, and to be honest, is the main reason why I started the work, is is the following. I will give more details on what is uniqueness for a stochastic equation and how one would understand this. But let me be a bit rough in the explanation. I will skip details. So we have our equation. I haven't yet written the equation. Now it's a good time to do it. So yeah, U plus minus plus U dot U plus pressure is equal to dissipation plus noise. Okay. And I write this as sloppy notation because I'm not writing the formal rigorous part. Okay, and so then we have an initial value problem. We are dealing with the incompressible fluid because it's in a way is the simplest one, and so this is a key term. And then we have an initial value problem, so an initial condition. So the solution of this is a process over an infinite dimensional space, which usually, when one works with the energy methods, this process is valued on H, which is essentially L2 of with value on R3 plus divergence free. For the whole 4 lectures, I will deal with the case of periodic boundary condition. Although everything I say works seamlessly in Dirichlet boundary condition, and maybe if you can make it work a bit more, you can also extend it to other cases. But we didn't do. I mean, whatever we did was on either Dirichlet or periodic, and so yeah, the totals. And as is simpler, I also had mean zero. I mean, the integral over the torus is zero, which amounts to say that I just work in a reference frame which is the same of the motion of the center of mass of the fluid. So I don't see the motion of the fluid has a rigid body. Okay, so I start with the initial condition, and this initial condition gives me a process. A process which is, well, not really, but let me, okay, which is, so a process which I can see has a random variable valued in the space, in some kind of Wiener space. So C is 0 infinity. Now I write something which is wrong, but first I write it and then I say why it was wrong, with values in H. This is unfortunately wrong because no one knows how to prove continuity of the solution in the energy space, and so usually one add say a weak topology. So this is now is correct. But if you don't know, if you are not really picky about that, you can just forget about this. And once is time you have to use this, you remember that I told you, and then you go back to your standard references like, I don't know, Temam or things, and then you realize why this doesn't work. So this is a law on this infinite dimensional space, right? So when we consider about uniqueness in law, what we mean is that given a solution and given an initial condition, there is only one probability measure on this space, which is the law of the process which solves the equation with this initial condition, right? And we don't know if there is only one. And if there is more than one, say we have two different solutions, one probability, which is the law of the solution of this equation with this initial condition, and then also we have another solution, which is again, they are different and they start at the same initial condition. So at time 0, this process is equal to this initial condition, and they solve the equation in some way that I will detail later. So the question is, what do these solutions have in common? They might be singular, and we will see later that it may happen. We may have the same equation with two different laws, and these laws essentially are singular. Or they may have some common component, or they may be equivalent or absolutely continuous with respect to each other, which is what I'm after. Because if I have two measures and one of the other has a density with respect to the other, that means that they are absolutely continuous. And well, and the point is that up to some, let's call it details, because I can't choose any two different solutions of the same with the same initial condition and say so. But if I choose this solution carefully in a way that is reasonable, the two probabilities are equivalent. And so it would be extremely meaningful to understand the properties of the mutual density of this different solution. Okay? Because this would give some hint on why two different solutions would be different or why they shouldn't. And so this would give us some information about uniqueness. So this is part of the work I did with Franco Flandoli some time ago. And you cannot choose any two arbitrary solution. You choose solutions which have essentially which are part of a Markov process. Okay. If we have a stochastic equation, I know you should know about what is a Markov process because in the previous lectures at least someone says the word. If I have a stochastic equation, say we have uniqueness and some reasonable other properties, this process, which is the solution of the equation, would be, if having uniqueness, this process would be a Markov process. Since we do not have uniqueness, we lose a lot of things. We lose continuity with respect to initial data, and we lose also the Markov property. You can recover both continuity with respect to initial data and Markov but I mean, it's a long work that I don't want to detail. Just keep to this. If we choose this solution as part of Markov processes, which we know they do exist, then these measures are equivalent. Okay, but then one would say, well, you are choosing some special solution. They may be just coincide, and the problem lies elsewhere. No, this is not the case, because I mean it's a reasonable theorem to prove that if you have only one Markov process which is solution of the equation, you also have one solution. I mean, so these solutions are special, but in a way, by means of them, you capture most of the, if not all, of the picture. So it's meaningful to look at this equation and at this special solution. This special solution says that they are equivalent. And so it's extremely meaningful to understand if these solutions have a density. Well, they do. If this density has some kind of special properties, or some special properties of these densities may give some hint of the problem. Okay, so this is my real motivation, and you will find some more details on in the notes about this. I didn't want to give too many details because it takes time. Okay, and so this is the end of my motivation for the work. Let me spend some words on the setting of the problem. I hope now you're convinced I can go ahead. And I should have taken half an hour, but that's fine. Okay. So, okay, what I said is we consider, well, let's say, setting. We consider Navier-Stokes equation with periodic boundary condition. So I will keep using some standard notation, which is is part of the. You find it in all these books like Constantin, Foyash, Temam, many others. And so let's say you can think of the torus as you just take the torus and you make it flat. So like the interval minus pi power 3. So at least in a geometrical point of view, they are the same, but I'm not a geometer, so for me, it's simply this one. And so on this, we consider L2 of the torus, and on this we have a natural basis, which is the one of Fourier series. And as I said, at the equation, I will add the condition of mean 0, which essentially amounts on the fact that the coefficient corresponding to k equals 0 is 0, which is essentially the same thing. And so here I would get the integer component vectors, but 0. Let's say this symbol, which I will change. Okay? And if I consider the Laplace operator on this, on the torus, okay, as in with Dirichlet boundary condition, this is a operator with compact inverse, so it has a series of sequence of eigenvalues, and so I can and eigenvectors, and the eigenvectors are essentially this one. But this is vector valued. Either I consider vector eigenvectors, or so I prefer to consider these as eigenvectors and have vectors. So if I consider the Laplace of ai kx, this is minus k square ei kx, And so okay. And since I also have a divergence-free condition, I can consider the subspace of L2 of the torus, which okay, I denoted by H. Okay, and since we are with periodic boundary condition, the fact that there is a derivative makes the definition of this space not that simple, because in a way, okay, only L2, the function do not have a trace on the boundary, but once we have a derivative, it turns out that the solution have a trace on the boundaries, and so one has to be careful about this, but okay, full details are in this standard reference I talked about. Then we can consider the space V, which is essentially H1 of the torus plus divergence 0. And so on. One can consider all Sobolev spaces of the Hilbert type, so H alpha. Again, plus divergence 0. We can look at these spaces in a different way, because if I consider this operator, that if I incorporate in the operator the boundary condition, so I consider the extension of this operator onto this space, now this is what is called the Stokes operator that Sundar was talking about this morning. So let's denote this by A. And so it turns out that all these spaces, okay, clearly V1 is equal to V. So all these spaces V alpha can be considered as the domain of some powers of the operator over 2. So this is positive self-adjoint, and so one can consider powers of the operator. So it makes completely sense. So this is the setting I'm going to use. So these are the bases. Sometimes it is not very convenient to use this basis, because then the equation, the components have complex valued, and so one can consider a real basis. In dimension 1, if we do Fourier basis, what we do, either we go with the Fourier with the complex exponential, or with sinus and cosinus. And then one can consider, in this case, also a basis of sinus and cosinus. I mean, it's easy to do this. I mean, with some, I will talk about this later. Okay, so we have the Stokes operator. And if we look at the equation, so the Stokes operator is essentially the Laplace operator projected onto the space of divergence-free vector fields. So a standard trick with which I think dates back to Jean Leray is goes back to Jean Leray, is to project the problem onto the space of divergence-free vector field. So to project directly the equation. So why? Because in the main problem for the Navier-Stokes equation is, or are, but they are two faces of the same problem, the divergence-free condition, or, if you wish, the pressure term. Okay? In the case of incompressible fluids, you can look at the pressure term as a multiplier condition to keep the solution with the constraint of the divergence-free. Okay? And that's why they are connected. And without the pressure, without the divergence-free condition, the problem of uniqueness is fine, is solved. It's been solved by Olga Dizenskaya in 1960 something. Okay, so you just drop the divergence-free condition, you just drop the pressure. What you get is an equation which has a unique solution. Okay, so there is really the problem, at least from an analytical point of view. So what we will do, we'll consider the so-called Leray projection. And we will project, hold the equation onto H. I will keep denoting by u the solution, and so I will end up with a stochastic equation, which will be actually A is the projection of minus Laplacian. I want it as a positive operator, but it doesn't matter. You can make it negative if you wish. And then you have here the projection of the nonlinearity. And by projection onto divergence-free vector fields, the pressure disappears, and what we get, we have a noise. Right now, I write in this way because I have a noise with some covariance. There's a reason to have a covariance. Sorry?
dt.
Yeah, you're right. But when I put dt, is the whole thing becomes more clumsy, and so I prefer not to. Well, I forget it, but it's better not to have it because it's clear. I mean, it's okay. And then the projection of this term. It's interesting to see that this term can be written in different ways. So this u times the gradient of u, which means sum over ij of ue derivative of uj over xi, can be also written as the divergence of the matrix u times u. And u times mu is the matrix with the elements ui, uj. And ij goes from 1 to 3. Okay? And so the projection of u times the gradient of u, which is usually denoted by b, and so I will stick with this notation because it's the one you find in several books. Is this one. Okay, and now I can put dt because now it's simple. So
what's C again? Is a negative power of A?
Now I come to the covariance. And so the divergence-free constraint is incorporated into the equation because all these terms are divergence-free. And so automatically all this is divergence-free, and then we will choose the covariance in such a way that this is conserved. And so the solution is, by means of this representation, is divergence-free. And now let's go to the noise term. One would like to consider, for instance, there are two good models for the noise. One is space-time white noise. I mean, why? Because essentially we had this term as a kind, either or as a kind of randomization of the equation, because it would make the whole thing simpler, or because we consider all these sources of uncertainty, like fluctuation in either in I don't know, in temperature or the other concentration of particles inside the fluid, whatever. So and we do not know anything about all these phenomena, right? We don't know how this fluctuation happens, and so space-time white noise would be uncorrelated components. Is kind of a model of ignorance. We don't know what happens, and so we do not assume any correlation, which is what usually one does, for instance, in first step of bias statistics, which, okay, I start with, I don't know anything, and then maybe I can make a better guess. But the first step is I don't know anything, and so I assume independence. And so space-time white noise would be a reasonable model in this direction. Another direction, which is more related to the physics of the fluid, says, well, that if some fluctuation happens, they do happen not at any scale. Okay, now I'm in a periodic boundary condition, and so I can look at this as waves in my Fourier analysis, and so these are frequencies. So the inverse are these are frequencies. Yeah, they are frequencies, and so I can look at it. So it is not possible that I have a temperature fluctuation at any frequency, right? It's unphysical. So it's much more reasonable that I have frequencies which are concentrated I mean, if my box of fluid is this size, I don't have its fluctuation at this size. So for very small frequencies, there should be no noise. For very small frequencies, there should be no noise as well, because we are going on the scale which are like an atomic scale, which the model is completely different. And so there should not be any noise at those scale as well. So it's reasonable that the noise should be concentrated in a strip of frequencies, which is neither too big nor too small. And the usual understanding is to have a noise at the scale which is a bit larger than the scale of dissipation, because then the phenomenon of dissipation, which comes from, I didn't write it because I keep forgetting, but is not the only, the dt is not the only thing that I forgot. And there is a viscosity here, which I can claim I took one, but it's not true. There is a viscosity, and this viscosity is part of a kind of a dissipation phenomenon. And at the level of dissipation, the fluctuation is not so more important. You can put noise if you wish, but it's a completely different physical story. And so the reasonable way would be to have a noise at the level of neither too big nor too small frequencies. And so this covariance should be something that concentrates the noise in this strip. And this means that this covariance would give a noise which is finite dimensional. But with the purpose I have, having a finite dimensional noise makes the problem extremely more difficult. And only by means of Mallaman calculus we can consider such problems. So with the finite dimensional noise, the problem is, as I already said, that it's hard to consider Mallaman calculus in this problem because we do not have a Mallaman derivative. So the whole idea here is to consider methods which do not use Mallaman calculus. Although this would be the best solution because this is the most reasonable thing to do. Okay. So what is a solution of this problem? We are dealing with a stochastic equation, which is also a PDE. So for PDE, we have usually weak solution and strong solution. And weak solution is a solution understood in weak sense, so as a distribution, for instance. And what is a strong solution in this case? Well, a strong solution in Navier-Stokes, strong solution means only one thing, which is usually you have a solution which is more regular, so regular that all the theorems of uniqueness or of regularity start working, and so you have a unique solution which is global and smooth. Okay, so you may find different notion of a strong solution in different books, but they all amount to this. I get something that under those conditions I can prove uniqueness and regularity. Okay. So I won't give details of this, but the idea essentially is. So a weak solution is a solution which we consider this has either a distribution, or since we know something about the problem, we can consider this distribution as actually part of a large, but at least a smaller space than distribution. For instance, we look at this term. Okay, we do not consider space-time white noise because there is a problem, a technical problem, which is crucial. And the crucial point is that if here we consider space-time white noise, the solution we get cannot be any better than the regularity that gives the space-time white noise. And the regularity that the space-time white noise gives to a solution is not enough to show that the solution is in L2. And once the solution is not in L2, there is no way to give meaning to the nonlinearity. The nonlinearity is a square plus a derivative. If I consider this as a distribution, integration by parts, you see, I can look at the nonlinearity also has a divergence of something. So if I multiply by test function, I can drop the derivative over the test function. And so here I get a product, u square. I cannot do any better. I cannot put the square on the test function. So the derivative is fine. I can get rid of it, but not of the square. And as long as I don't have a function here, which for instance is locally integrable, and that means L2 loc, there's no way to give meaning to this term. And so that means that if I have a space-time white noise, the regularity of the solution is not enough to give a meaning to this.
So by space-time white noise, you mean derivative of Wheeler?
Yeah, if you wish, you can consider it as in this way. So yeah. There are several ways to consider this. My favorite is to just consider the sum with the coefficient 1 of yeah, cylindrical, if you wish. And okay, so the square does not give a meaning to this. And this is not a peculiarity of dimension 2, dimension 3. You go in dimension 2, it's the same problem. Okay? And you can do something in dimension 1, but in dimension 1, the divergence part is meaningless because of it. And since this is the main point, while having a one-dimensional model is not very exciting, unless you find a different way to recast the problem. Actually, there are some models which are considered a one-dimensional model of three-dimensional Navier-Stokes equation. Yeah, sure. You know, all these people, sorry? Like one-dimensional problem that say have the bad features of the three-dimensional Navier-Stokes equation. You know all these. I don't remember. I can tell you later. I mean, once I remember. And so what we do here in most of the part of the work, unfortunately, we do not consider these to be valued in a finite dimensional space. So we will put assumption on these that make the whole thing work. Most of the time, like it was already pointed out, I will think that this covariance has some inverse power of the Laplacian operator for a few good reasons. One is that the equation is simpler if this operator and this operator commute. Okay? And if the two operators commute, then they have the same eigenvectors, and then I can write this in a way. And the other thing is that if I write this as inverse power of this operator, I have a fine tuning of the decay of the eigenvalues. And the decay of the eigenvalues is a key point in regularity, because the smoothing properties of this operator depends on the decay on his own eigenvalues. And since you consider that we are working with Fourier complex exponential, so the decay of the coefficients immediately means regularity. I know a function is h1 if the coefficient decay at least has 1 over k squared, and this has to be summable, and so on. So this decay means regularity. So by getting an inverse power, you have a good control on the regularity of the problem. And that's why it's simple. But you know, the problem lies elsewhere. So I like to assume easy assumption, because I don't want to make my life complicated. Okay, so this is the equation. I think I introduced all terms, so it's fine. And so what is a solution? As I said, okay, we assume that the covariance is good enough so that what I will going to write is meaningful. So a weak solution in this case is okay, and now this weak is, I should write weak square, because I will consider a weak solution in both in terms of PDE, but also in terms of stochastic analysis, stochastic differential equations. And then I will tell you what is the problem. Okay, so a weak square solution, is a probability space and processes WT, T, and UT 0. So such that this equation holds in distribution, but we can do a bit better. So for every test function, for a test function where I introduce these spaces, and so I take a test function in V2. So I consider so ut minus u0 scalar product with the test function plus this term, and this time by integration by parts, the second derivative goes on the test function. And same for the nonlinearity, because the nonlinearity is the divergence of some product. So this divergence goes on the test function. And this BU, I understand it as BUU, and these are some properties which probably you already have seen in the previous week, or maybe 2 weeks ago. And so this is scalar product of BU phi U. This is essentially integration by parts. Take this divergence and put it over the test function. Maybe I should put a minus here. So this is equal to phi, see a half W. So, and processes this and this, so such that this happens, and sure, obviously, and W is a cylindrical linear process. On H. Well, sure. The regularity you need here is that is integrable, and so what you need here, what the regularity you need here is that
what you need.
what is needed here is that okay, you need if you look at these different terms here, you multiply u by a phi, and so you need essentially that this has to be, this asks for L1 of in H, and by this you get L2 in H, a bit less, but let's say L2 because there is U, and by this you need a evaluation, and so you need essentially continuous in the weak topology, so with values in V minus 2. Yeah, essentially. But you don't really need much. You need essentially L2 with values in H, continuous with values in V minus 2.
But if U is only in H, the identity which you wrote in line 3 is then true.
Which this one. With this one. Wow, definitely not. What do you mean by this is true? Well, if U is L1, L2 lock, okay, there is also regularity in time, but let us forget about this. If U is L2 lock, well, this is correct.
That term is correct. That term makes sense.
The term makes sense, has a distribution. I mean, it's, well, it makes sense as a distribution. If U is L2 lock. Because I multiply with the test function, and what I get is this one. And if U is L2 and phi is good enough, this makes completely sense. Sorry? This one. Oh, okay, yeah. This is a Wiener increment. So when I integrate in time, I get the random variance itself. This you should consider here. I always consider covariance which is state independent, so it does not depend on U. So all integrals go directly over the W. Sure, one can consider this problem which one has a covariance which depends on the solution, but again, I stick on the simplest assumptions. And so the covariance is does not depend on the solution. This is what we call additive noise. Okay. And did you ask? No. Are you satisfied with the answer or? Okay. Yes. But anyway, if you consider that if U is L2 lock, here is fine. This is well defined. Well defined where? In some space like H minus 2. So, well, actually you need a bit more, a little bit less than H minus 2. Here is H minus 2 because I have also this term here.
You cannot take any limit in that, right?
Yeah.
Because it's,
okay, now.
U squared is L1, so it's not, you don't have any compactness to take the limit. So.
Yeah, the point is that you cannot do much with such a solution. So that's why all these people on the last line are a bit say, okay, what this guy is doing? Does he really claim that he can do anything with only this solution? No. So relax. I'm not claiming this. This is a weak solution. The weakest notion you can give to the solution is this one. Actually, in the Navier-Stokes field, someone used the notion of very weak solution. But then you may add some other things. One thing that is nice to consider, and you have already seen this in some previous lectures, is the energy balance for the equation, right? And if you want to consider the energy balance, there's no way you can do this with the regularity I've given here. And so you have to assume some more regularity. And the key point is the proof of Leray is that you can assume this more regularity, and you can actually also prove that there is a solution with such regularity. And these are the so-called Leray-Hopf solutions, which are a bit stronger than weak solution. But now, the other thing I want to point out for this weak solution is that we have a weak square here. So the square dominates in this. Why is weak square? Because this is a weak notion of solution also in terms of probability. What do I mean? Let's write again this. We have a weak solution if there is a probability space, if there are processes, the solution and the linear process. Okay? So the natural notion of solution is I have some data, I give the data, and I obtain back a solution. Does not work here because unless I consider as data the initial condition, okay, and the statistics of the noise, not the noise itself. Okay, if my machinery is I give you a noise and then you give me back a solution, this doesn't work with weak solution. The only thing I can do is I give you the distribution of the noise, and then you can give me the distribution of the solution. And this is a weak solution. I give you the distribution, then you find a way to get somewhere a noise that makes the whole thing work. And this noise you give the right distribution by means of the covariance. And this gives a distribution because now there is a process and there is a probability space. Essentially what we have here is a probability distribution of the solution. So a strong solution in a probabilistic sense is a different story. It's the story I told first. I give you a noise, and for that noise, you give me the solution. Okay? So we will come back to this. That's why I'm insisting, because in terms of a Doob mutability theorem, a strong solution is something that you get as a function of the data if you consider noise as a data. I have a noise, and I have some function, so some way of manipulate this noise to give me a solution. Here we have a weak solution. That means that we have some way to produce a distribution by means of a data distribution, so by means of the distribution of the noise. Okay, since the space-time-wide noise has an obvious distribution, the data is all here. So in a way, it's the same. From data, we get the solution. The point is, which are the data? Okay? So we have weak solution. Weak solution means this. If we want to do something on the equation, we need also energy balance. Okay? There are several reasons to consider the energy balance. One is, well, it's physically reasonable. The energy does not get created somewhere. Unfortunately, this energy balance in dimension 3 is an energy inequality, and so we do not know where part of the energy is going, and so this is a bit unphysical, but at least not as unphysical as creating energy from nowhere. So an inequality is anyway better than nothing. And this energy inequality, which I can write somewhere, also has another role, which from the point of view of the mathematical analysis is also crucial. Okay, let me, how do you get the energy inequality? Well, first, you, in a way or in another, you consider a solution, so l'Aero-Hop. So l'Aero-Hop solution is a weak solution such that the energy inequality is satisfied. Leray because he was pioneering the work on mathematical work on Navier-Stokes, and Hop because Hop was essentially he found a way to work also with the bounded domain. Because in the way Leray was working the whole space, and that's why I got Leray-Hop holes. So how do you get the energy inequality? Well, you take the L2 norm, and since we are in with the stochastic equation, we would like to consider the derivative in time, but we have a noise, and so what we do, we use the Ito formula. Okay, so we apply the Ito formula to this. I immediately stop the last line. Sure, this Ito formula cannot be applied directly on the equation because we do not have enough regularity for the solution to prove that the Ito formula can be applied. Essentially, this is part of what I said before. U is not regular enough in H. So we could use the Ito formula in some larger space, so H minus 100, but then this thing does not make sense. So we are in trouble. So what is the solution usually? You prove that there is a solution which satisfies an energy balance. So what you do, you use some approximation method for the solution, you prove the equation, the balance on the approximation, and you get in the end the balance in the original problem without doing a Ito formula directly on the solution. But we will do this anyway, because we are sloppy. So we apply Ito formula on this. So this term, due to the fact that A is self-adjoint and essentially is the second derivative, gives us U norm in V, or in H1 if you wish, square. And this is the term here. And then there should be the term here, but as you have already seen, if I do multiply U by the nonlinearity of Navier-Stokes in L2, this term disappears. You have seen this, right? No? Yes, okay. No. Oh, yeah, at the third week, it's L2. So I write it anyway, my UBU product in L2, and then this has to be equal to scalar product C, scalar product of integral, no, okay, no integral, U times C a half dW, and then there is a correction term, plus a half, no, plus, yes, plus nothing because I forgot the 2 here, plus the trace of the covariance. Okay. So, as I said, this term disappears because we are in L2. And once this term disappears, we are in business. Why we are in business? Because just make some computation. U is square. U is square. Fine. It also has whatever is this. There's a plus here, so it's on the good side. And here, these are the data. But anyways, in terms of powers of U is power 1, and this is a number. Fine. And without this being 0, we would be in extreme trouble because this is U. This is the nonlinearity. Being nonlinearity is nonlinear, and this is power 2. And since it's power 2, this whole term is of power 3. And since this is of power 3, if I want to do any simple thing like a Gromwall lemma, like this morning, I wouldn't have any hope because this is of power 2, this is of power 3, and we do not know, well, this is 0. But this term has no sign. We will see that if I do exactly the same thing with the norm in H1, all thing applies the same way. The problem is that this is not 0. Okay? But this is 0, fortunately, and then we have the energy balance. This disappears, and then we have T square plus 2 times the viscosity is equal to 2 times from 0 to T U half W plus the trace of the covariance times T. And unfortunately, not yet. We have a smaller equal here. Why? Because the only way I can prove this is by means of an approximation. And good approximation, let me pass in the limiting this term. And good approximation, let me pass in the limit in this term. But unfortunately, when I try to pass in the limit in this term, I get an inequality. Oh, and then here there is the initial condition. Okay. I forgot it, but while you were asking that, I wrote it. So this time, okay. And if I do this, these are the data. If this is finite, and if this is finite, and I know how I can treat this because this is a martingale, and this quadratic variation is U squared, but measured in a topology which might be weaker than this one, and so in the end, by means a bit of a beta stochastic analysis, it's something that Shizlav, it's the same ideas that Shizlav was showing this morning, because then this is a martingale. You know, if we want to essentially show that something is finite, and so we need that the quadratic variation of this term should be finite. So we apply a stopping time argument, and everything goes through. And so on this side, essentially we have something which is finite, and also this is finite. And so what we get is that U is L infinity uh, 0t with values in H, and is L2 0t with values in V, and this is for every t larger than 0. So we can update, and an array of solution is a weak solution with this regularity and this energy balance. Okay, and then you find a plethora of different definition of L'array-off for the stochastic setting, because since you consider the energy inequality as part of the solution, then you define it in the way which is more useful for you. Okay, I mean I gave at least 2 or 3 different definitions in different papers because they were simpler to work in that way. Most of the time they are the same. Sometimes they aren't, and then you can, but essentially it's the same. I mean, the idea is that you want the energy inequality to be true. Okay? And that is a solution. What is a strong solution? A strong solution is something which is more regular. For instance, standard in without noise is L infinity of H1, L2 of H2. So why I mean this standard without noise? Because when we add noise, so we add an external forcing, and the regularity of the solution depends on the external forcing. There is no hope to have a solution which is H2 when the external forcing does not allow for an H2 solution, okay? So, and that's why I gave a definition of a strong solution as a solution which has the regularity that allows to prove uniqueness. And regularity, as much regularity as the data allows. Because, again, if the data is not regular enough, we cannot have a C-infinity solution, and then this term gives me, I don't know, H1 trajectories. It's no hope. If U is C-infinity, everything here is C-infinity, I cannot match this H1, but not any better. Okay? So, for us, a strong solution is something that is regular. How do you get strong solution? Well, for instance, you can do exactly the same here. You do the energy inequality, well, not energy, but you do the same Ito formula on the H1 norm. The H1 norm does not allow for this term to disappear, and so you have it. And if you do this on let me give a very rough explanation. Now we do the same in H1, and then here gives us A of U in L2. So this is the H2 norm, and then we have okay, this. Let me call it. There is a martingale term that now I want to neglect because I don't want to also to handle the difficulty that come from this part, but once one does this, the idea is again to work with, for instance, with stopping time and so on. And then we have a trace, but this trace is of not of the covariance C. We have to take into account that we are doing the Ito formula in H1, and so there is the trace of the operator AC. So we're asking for something stronger. And then I put the nonlinearity here. This time the product is in a H1. Okay, now let me neglect this term. Let me forget about this. Once it's finite, this does not add any more difficulty. And this term, this is quadratic. This is, okay, this one. So this goes essentially like, and you can prove it actually, U H1 power 3. And once you do this, you have a U square on one side, U6, sorry. There is a reason for this, but because you can use this term to smooth a bit this, but okay, in the end you end up with 6 or 6. I can, if you are interested, I can give you the detail on this computation. And so this is U square, this is U6, so it's U square to the power 3. That's why I wrote. So it's like having a ordinary differential equation, x dot equal to x cube. And we know that with this, with the initial condition, with this solution, explode after a finite time. So there is a blow up. And this means that if we do a Ito formula in H1, we can do this only for a short time. And this essentially is the basis, the idea to prove that there are strong solutions for a short time. Okay, please.
The right hand side, after the martingale term.
Oh, the trace is the trace.
AC.
AC is the operator A and the operator C.
You're multiplying by AU, A half U square, so you're definitely.
So this is the Ito correction, but it's an infinite dimensional. So you have to take into account that I'm working with topologies. Okay? Okay, and that's essentially the bulk of the idea that you may prove existence of a strong solution. Because then they are bounded in H1, L2 in H2, And that's a strong solution. And once you have a solution which is bound in H1 and L2 in H2, this is a strong solution. And is unique. Well, and now it's the main point, which let us understand why we like to have the energy inequality. Because strong solutions are unique, well, are unique in the class of strong solution, but they are also unique in the class of Leray-Hopf solution. So if I have a strong solution with some initial condition and the Leray-Hopf solution with the same initial condition, at least as long as the strong solution exists, they do coincide. Okay? So that's why having a strong solution is crucial. Having the energy inequality is crucial. Because at least for a short time, for every initial condition which is regular enough, you see, since I'm doing Ito formula here, the initial condition would be initial condition in H1. So I need something regular. So as long as there is a strong solution, this is the unique solution. Whatever. Either with weak or with strong solution. This is so-called weak-strong uniqueness principle, which was proved, I don't know, I think this was Prodi and Serrin that got this idea. Yeah, right? Yeah, this is formal. So in the end, well, actually, once you have a solution, this is an inequality, because you are proving it with a solution which is smooth. And so this energy inequality is going to be extremely important, essentially, on Wednesday. Okay. So now we have only a quarter of an hour, and that's not good. I want to, okay, now we have an idea on how is the equation, which are the most important part, essentially the energy inequality. What is I wrote it here. What is a solution? Let us see. Let's see the problem of reference measure. Yeah. Okay. I only a quarter of an hour. Okay. So let us go now to the main part. Now we know what is a solution. We know what is the main subject, and we would like to show that there are densities, and we don't know which kind of reference measure we can use for such densities. And that's why from tomorrow on we will go to projections, to finite dimensional functionals of the equation, because we don't know which kind of reference measure we can take in infinite dimension. Let me start with an example, which is essentially the main point. So now let's switch to the problems of reference measure. In the notes, all I'm saying is written in more details, sometimes in full details, but not all of it. And in the end, I managed to get about 100 pages. So you don't find full details, but enough details for all I said. So you can go through the notes once they will be available. Hopefully, this time I didn't remember. I didn't forget the attachment, and so. Yep.
I have a question which probably you will speak about anyhow, but just so you consider you want to consider density of one weak solution against another weak solution.
No. Once I have finite dimensional projections, I consider directly densities with respect to the Lebesgue measure. And in some cases, if they are both equivalent to Lebesgue measure, they are both equivalent with each other. Okay. And but in principle, I don't know how is the density. You know, all the ideas I will explain, and then actually this is part of what I'm saying now. I won't be able to say, to know how is the density, okay? But this is part of what I'm talking about now. Well, I will explain why this is also another problem. So the problem is how do I choose a reference measure for to get a density? Okay, in finite dimension I said Lebesgue is the obvious choice because we know that, and also because it's flat, so there is no bias. do we have densities, for instance, for stochastic equations? So there is a full theory. For instance, one way is through Malevin calculus, another way is through Hermander theorem, but they are two parts of the same problem. Let's consider a very simple equation. I will always consider additive noise, because with the sorry? Yeah, I know. I wrote it. Okay, let's consider this. And with f, I choose, so f, and f is the derivative of some f prime. Just think at f as a convex function with a growth at infinity. For instance, f is equal to x squared. So all the reasonable assumption in case of you can even take not convex, but like a double well of things. It works anyway. But let's stick to the convex growth at infinity, so x squared essentially. And so this would give Horstein-Uhlenbeck. If we consider this equation, well, then we can find a very reasonable reference measure, which also has a reasonable meaning, because by the choice of the drift, we know that, as we learned this morning, that there is an invariant measure. And the good thing, the good news about this problem is that we can exhibit explicitly an invariant measure of this problem. Because an invariant measure of this problem is essentially this one, E minus f of x, where f is the primitive of this function. I'm working in one dimension. And, well, by the assumption I took on f, so it's growth at infinity, this is, if I integrate over r this is finite, and so I can normalize this, and I get an invariant measure. And since I'm in one dimension, additive noise, this problem is also Stromfeller, and this allows me, we know about that because you were told this morning. That's very good, because I didn't want to talk about that, but now I know you know that. And one consequence of being Stromfeller is that the laws of the solution at any time are equivalent measures. Okay, so this is very good news. And this extends to the invariant measure as well. We are in a very simple situation here. So all these things are very easy to prove. And that means that the solution of the solution at any time is equivalent to this measure. And so we can look at densities with respect to this measure. With a bit of computation, we can even give an explicit, well, almost explicit function. But I didn't do that, because
So this is what mu dx is equal to times d.
yeah.
d mu is equal.
I'm starting to anticipate your question. So this is an explicit invariant measure. So it has a meaning for the equation. We're not choosing some measure that by chance is working, but has some. No, we are choosing the invariant measure. So after some time, the solution will look like, at least in distribution, has this term. How do we know that this is an invariant measure? Because at this level, I only said, okay, this is an invariant measure. So either you believe me, which also can be a good solution because there are 520, or you do the computation. And this time we do the computation. How do you prove that this is an invariant measure? Well, okay. We have a solution, xt, and we consider functional of this solution, so phi of xt, and then we consider expectation, and we know that fixed t, by running over all phi in some reasonable set, continuous and bounded or Lifschitz bounded and so on, we can characterize the law of xt, right? Because the law of xt is a probability measure on R, but the probability measure on R can be seen as a functional over a continuous and bounded function, and so by means of the state function, I know completely the measure. So to prove that this is an invariant measure, what we do? We show that if x0 is has this distribution of the invariant measure for any time, this thing has the same distribution. And so these things are stationary. So this quantity does not depend on time. Okay? This is not a real proof. The real proof goes through some different argument. But in the end, the bulk of the computation is this one. So what we would like to do a derivative of this and show that this is a bit more difficult. So what we do, we apply Ito formula to this term. Oh, okay, we should be able to use the Ito formula. So this test function should be C2. Fine, because in the end, I will have a formula which does not contain derivatives of phi, and so this should be fine. Okay. If I apply the formula to this, I have phi of xt dxt plus a half pi second of xt, and in dt, because and I won't get an invariant measure because I should put here square root of 2, because otherwise I have to put a temperature here. Well, anyway, and so this alpha is not here. Let me put square root of 2 here, so I don't have the half and things, and then this is an invariant measure, because this is a kind of invariant measure of Gibbs type, and then if here I have a coefficient, this corresponds to an inverse temperature. Doesn't matter. Okay, so we do this computation. Let me assume, for simplicity, that x of t has a density, and let us see which is the equation satisfied by the density. So let us assume, this is an assumption because we have not proved this. Xt has density pt. Okay, so we do this, and then we have minus phi prime of xt, f of xt, dt plus square root of 2 d phi prime of xt dwt plus the second of xt. Okay, now I take expectation, I integrate so that in the end I can get the derivative of the expectation. Or if you wish, I take expectation of the derivative, and then I switch expectation and differential, which is very bad, but in the end is what I get. So this is going to be the integral over r. No, this is expectation of phi prime of xt, f of xt, dt, plus e second of xt. Okay. No, this comes from integrating, taking expectation, and differentiating again. But in the end, the result is here. Okay, now let us use that the p has x has a density. And so this is the integral over r of the density times this part. This is the density of this one. And so this is, they differentiate in time. And so the time integration is not. I said it's bad, but it's something. Okay, and this is the expectation once we know that there is a density. So now what we do is we integrate by parts. As I promised, I will make all derivative of phi disappear. So I integrate by parts here, and so I get integral over r of phi of x times pt f derivative minus, now I integrate twice in time, so that the minus of the integration by parts, there are two minus, and so they disappear, and so I keep this minus. Integral of phi of x dxx. Okay, so I come back here. So in the end, what I have is derivative of the t expectation of phi of xt is equal to integral over r of phi of x times PTF x. Can you read it or not much? Okay. Or this thing is exhausted after 1 day of lectures. Integral over r of minus pxx plus ptf of x. And this, okay, so we want to show that this thing is an invariant measure. Why? Because if it is an invariant measure, since this problem is from Feller, all laws are equivalent to this one. And so we have proved that there is a reference measure which is meaningful. So the goal is to prove that this is an invariant measure because then this is the good reference measure. So to prove that this is an invariant measure, we wanted this to be 0 for any phi. And this means essentially that this has to be 0. So what we got is, we got an equation for the density, which is the Fokker-Planck equation. And now is a matter of differentiate and replace. If you do the computation, you take this function, which is the density of the invariant measure, you put it here, and you discover that if p is equal to this one, this term is 0. Unless I made some mistake with the sign, which might be. Try with either with minus plus, or with minus or plus, and then you see which one is good. Because yeah, I should have done some error with the sign because here I get. But anyway, so we'll try with a plus if with minus doesn't work. That means that if you start with this initial distribution, at any time you're going to have a 0 here. And this is a good reason why this is an invariant measure. And if this is an invariant measure, this is the reference measure for this problem. I do this in finite dimension so rather than in R, in RD, and I get the same, as long as I have space-time white noise. Why? Well, because if I don't have the space-time white noise, there is some problem, and I'm not able anymore to show explicitly an invariant measure, which does exist anyway. So we still have an invariant measure, so we have still equivalence with respect to the invariant measure. We have some information on the invariant measure, but we do not have an explicit function like this one. We go in infinite dimension. We go to the problem, for instance, du is equal to Laplace of u minus some say Gateau differential of f of u dt plus square root of 2 dw, where w is a space-time white noise. I still can show that there is an explicit invariant measure over time, so I won't do that. But we still have an explicit invariant measure here. So space-time white noise is also good by this point of view. It does not introduce skewness in the components. As long as we do not have a space-time white noise and we have reasonable nonlinearities, I do not know any case in which you have an explicit invariant measure. Well, you can go to systems which essentially are like this. I mean, you have some particle systems or models in which you have explicit invariant measure, but they are usually of Gibbs type. And so in the end, the class we have captured here is the good one. Problem, we cannot use space-time white noise in our problems, not even in 2 dimensions. This is not completely true because there is a work of D'Aprato and Debush. They showed that they can work with the 2-dimensional Navier-Stokes with space-time white noise, and they have an explicit invariant measure, which is again of Gibbs type. So this is this. Once we do not have these kind of things, we may have an invariant measure.